All right, so in the last video, we looked at exponential functions and how they applied to financial type problems with our periodic and continuous interest. So in this video, we're going to look more at these exponential growth and decay models more generally and how they can be applied to more situations. So right here, this A of t function, this is going to be our exponential growth or decay model. So this is similar to what we saw with the continuous interest with the financial information. So A naught is our initial amount. Okay, that's similar to the principal that we saw with the finance. R is the growth rate, or this could also be a decay rate. When you're talking about this in more general terms and not in terms of just finance, you can have something that's either growing or decaying. So as a general rule, you're going to get growth if your R value is greater than 0, and you're going to get decay if your R value is less than 0. So a negative rate will give you decay, right? And that would be something like a radioactive substance, if it's decaying over time, would have a negative rate. All right, and then T is our time on this one. And A of t is just the amount that you have after that particular amount of time. So the first example we're going to look at with this more general model is population growth. So if we look at this example 4, it says in 2001, the world population was 6.2 billion. So world population was 6.2 billion. If the annual growth rate averaged about 1.3% per year, we want to write an exponential equation that models this situation and then use that model to estimate the population in 2025. Okay, so let's think about what we have here. So it said that in 2001, the world population was 6.2 billion. So that's our starting value. That's our initial amount. So we know that A naught, or A sub 0, however you prefer to say it, is 6.2. All right, now we also were told here that, well, let me say here, I'm going to be letting my amount be in billions. So I'm just saying 6.2 instead of the 6.2 billion, but we'll know that things are being measured in billions. Okay, so our growth rate is 1.3%. And of course, we have to change that to a decimal. So that would be 0.013. Okay, and it's growing, so it's a positive rate. And we are looking for the population in 2025. Now keep in mind here that our starting year is 2001. So 2001 corresponds to t equals 0. So from 2001 to 2025, the difference there is 24 years. So we're looking for when t equals 24. Okay. So let's go ahead and build a model. So this is the general format that we're fitting this to. A of t is equal to A naught times e to the power of r times t. That's our general exponential growth or decay model. So we can plug in our particular pieces. So our A of t would be equal to 6.2 times e to the power of 0.013 t. Okay, so this guy right here, this is our growth model. And notice that I didn't actually plug in a value for t yet, because a growth model should be a function. So it needs to still have the variables, the t and the a of t in it. Now we can use our model in order to estimate this world population in 2025. So now we can substitute it in. So we're looking for A of 24. That'll equal 6.2 times e to the power of 0.013 times 24. All right, and then if you plug that into your calculator, you will end up with approximately 8.5. And then remember, this was in billions, so 8.5 billion people in the year 2025, according to our model. All right, so this is the general idea with these exponential decay and growth models. Let's go ahead and take a look at another example. This time we're looking at bacteria. All right, so we have a bacteria culture starts with 8,600 bacteria, and after 1 hour, the count is up to 10,000. So first thing we want to do is find a function that models the number of bacteria after 10 hours. Okay, so let's think about what we have here. So a culture starts with 8,600 bacteria, and then we know that after 1 hour, we're up to 10,000. So the starting bacteria, that is our initial amount, that's our A naught. But then the second piece of information, that after 1 hour, the count is up to 10,000, this is basically just giving us a point. After 1 hour, our count is up to 10,000. So that's just a point that we're going to use in order to build this model. So notice the thing that we're not given this time is a rate. Okay, we're not told what our growth rate is. So we're going to have to figure out what that rate is based off of the initial amount and then how much it has grown to after an hour. This one's going to be a little bit more work to have to solve. Okay, so we're starting off still with our same exponential growth model that we used before. A of t equals a naught e to the power of r times t. So let's go ahead and plug in what we know. Okay, so right now, all we have for our model is a starting point, 8,600, that we can plug in. But like I said, we don't know a rate. But what we can do is we can plug in our point in order to solve for our rate. So the 1 is going to get plugged in for t, and the 10,000 is going to get plugged in for a of t, and then we can solve for r. So we'll have 10,000 is equal to 8,600 times e to the power of r times 1. All right, so now we're just trying to solve for r, okay? So we have an exponential equation. Just like we've done in the past, in order to solve this, we're going to isolate our exponential term. So divide by 8,600 on both sides. And if you plug that in, 10,000 divided by 8,600 gives you 1.16279. My suggestion for you on these, when you're solving for these growth rates, you're going to be coming out with some small decimals. So it's important that as you go through these, that you don't round your numbers too much along the way, because if you do, it can make a significant difference in what your final answer is. So I would say keep at least 5 decimal places on these, if not more, because you don't want your final answer to get too far off because you've rounded too much along the way. Okay, so we got the 1.16279, and that's equal to e to the power of r. And then now that we've isolated our exponential term, we can rewrite this in log form. And remember, a log with a base of e is a natural log. So this would be the natural log of 1.16279 is equal to r. And then plug that into your calculator, and you get approximately 0.150823. So our final function here, we end up with a of t is equal to 8,600 times e to the power of 0.150823t. That is our answer for part A. All right, so part B says now find the number of bacteria after 2 hours. All right, so 2 hours is a t value. Let's say t is equal to 2. So we're just going to plug it into the function that we just found in part A. We're looking for A of 2. So that'll be 8600 times e to the power of 0.150823 times 2. Plug that into your calculator, and we'll get approximately 11,628 bacteria. Now, when you plug this into your calculator, you are going to get a decimal, but since we're talking about bacteria here, you're not going to have part of a bacteria, so you're just going to want to round your answer to the nearest whole number. And you would do that with a lot of population growth type examples. So if you were looking at people, you would do the same thing because you can't have part of a person. You would round it to the nearest whole number. So make sure you're thinking about what you're finding and if your answer actually makes sense in that context. And a lot of times that's going to mean rounding to a whole number. All right, part C then says, after how many hours will the number of bacteria double? Okay, so we know that we're starting with 8,600 bacteria. So if we're looking for our bacteria to double, that means we want our A of T to be twice 8,600, so that would be 17,200, and we're looking for after how many hours, so we're solving for T. Okay, so we can substitute this into our equation. We're looking for 17,200 is equal to 8,600 times e to the power of 0.150823 T. All right, and now we're trying to solve for T. So once again, we're solving an exponential equation. So we're going to isolate our exponential term by dividing by the 8,600 on both sides. 17,200 divided by 8,600 is just 2 because it was doubling. And then once you isolate your exponential, rewrite your equation in log form. So that would become a natural log of 2 is equal to 0.150823 T, and then divide by your rate, and we get our T value of approximately 4.6 hours once we plug that into our calculators. Okay. All right, guys, so I'm going to go ahead and end this video here. I'll do one more video for you on this exponential modeling stuff, and we'll be looking at radioactive decay and the idea of half-life. So keep watching for more examples.